I'm Benedetta. I'm doing a PhD in Rome, in Italy. And today I will tell you about the transition edge sensors to detect low energy electrons, so not precisely neutrinos. But now we'll do some steps back to try to understand why I'm talking about this, why I stated chasing the CvB and the neutrino mass, and why this is an important technology to improve in order to achieve these goals. Okay, so this research relates to the Ptolemy experiment. Ptolemy wants to measure the value of the neutrino mass, so the absolute value, and to detect the cosmic neutrino background, which are all the relic neutrino decoupled from ordinary matter just 1 second after the Big Bang. So detecting them could provide a unique snapshot of the primordial universe, but it is a real challenge as they have extremely low momentum. So the idea of Ptolemy is to study the beta decay spectrum of tritium as it gets modified by both neutrino mass effects and relic neutrino capture on tritium. Now, these modifications are equal to the value of the mass of the neutrino, so we're talking about milli-electron volts. That's why having an excellent energy resolution is crucial to try to distinguish them in this final spectrum. And the idea of Ptolemy is to load the tritium on a solid-state target made of graphene, and then slow down the electrons coming from the beta decay and the relic neutrino capture, and finally measure their energy. One of the options is with transition edge sensors. So this is the framework. And the Ptolemy goal in terms of energy resolution to hope to see such tiny modifications in the spectrum is 50 milli-electron volts on electrons on 10 EVs. So now that the framework is clear, I hope, we can talk about transition edge sensors and electrons to perform these measurements. So transition edge sensors are superconductive calorimeters, and superconductivity exploits the strong dependence of resistance upon temperature. So starting from a normal state resistance, lower and lowering the temperature, in a few milli-K, we reach a superconductive state in which the resistance is 0. And this is the superconductive transition happening at the critical temperature, which is typically of a few hundreds of milli-K. So to operate a superconductive device, we need to be in a cryostat. So a TS is a superconductive film operated at its superconductive transition, where it is more sensible to changes in its temperature. And when a particle arrives on a TS, it gets absorbed, so the device heats up, and even slight changes in temperature lead to measurable changes in resistance. Transition edge sensors have been traditionally used as photon number resolving detectors, as they have an astonishing energy resolution, and in particular, we can distinguish how many photons hits them simultaneously, basing on the amplitude of the signals. All nice, but here the question is, can ATS detect electrons? Can we manage to use them for Ptolemy? And we have to find an electron source which can be placed inside a cryostat to test them. So typically, the electron source exploits photoelectric effect or thermionic emission, but they're not good in a cryostat because they or produce some background which is indistinguishable from a noise, or they produce heat. So our solution is to use field emission. Field emission is a quantum process, so it does not need nor produce any heat. And in field emission, by applying an high enough external electric field to a metal, we can extract some of its electron by which quantum tunnel the surface potential barrier. So it is good to be used in a cold environment. But we have to say that to generate field emission, extremely high electric field have to be applied. So in particular, if we want to extract electrons from a flat surface, we need fields higher than 10 to the 7 volts per centimeter. But if we use pointy surfaces, so surfaces with some nanostructures, we can have some local field enhancement factor due to the tip effect up to 10 to the 4. And this is precisely the trick we use, because like that we can extract electrons with much lower electric fields. And the nanostructures we decided to use as field emitters are carbon nanotubes. So carbon nanotubes are graphene sheets rolled in straws with diameter of 20 nanometer, let's say, and length up to hundreds of microns. We grow them vertically aligned to each other, as you can see here in this picture, in this kind of forests. And we grow them directly in our university in the Titan lab. And the idea is that if we place a sample of nanotubes in front of the detector, we create kind of a parallel plate capacitor geometry. And by applying a voltage to the nanotubes, keeping the detector at ground, we generate an electric field that, once overcome a certain threshold, can extract electrons and then accelerate them towards the device. Now, a typical behavior, a typical trend of the field emission current is exponential with respect to the electric field, which is in this case equivalently to say to the voltage of the nanotubes. And this is a threshold process. In our sample, we just need hundreds of volts to have electrons. But we also have to keep into account the fact that the kinetic energy of these electrons once reach the transition edge sensors is proportional to the voltage we give to the nanotubes. So we have a little bit of constraints here. This was the electron source, but now let's go to our setup. The experimental setup of these measurements is called MIC, which means mozzarella e carrozza. It's a typical Italian dish to which it resembles in shape. And so the idea is that we have a copper plate of 5 centimeter per 5 centimeter on which we place the TES, which is grounded. And our TES was fabricated in INRIM in Turin, where I made all this research. And it is a square bilayer made of titanium and gold with niobium wirings. It has a side of 100 microns, and it is a critical temperature of 84 milli-K. So here is the TS, in front of which there are the carbon nanotubes on another copper plate. So they are glued in front. And our sample of nanotubes is 3 millimeter per 3 millimeter. And here it is a picture. You can see the nanotubes like grouped in some tufts. And in between the two plates, there are some sapphire spacers to guarantee electrical insulation, so not to short circuit everything. And this is a picture of the MIC mounted on the cryostat. Okay, so once all this setup was completed, we applied a certain potential to the nanotubes, and we started seeing signals on the TES. Now, there is a comparison between the field emission current of the sample of nanotubes and the signal rate we saw on the device. Now, the black solid line is the field emission current, which was obtained simply connecting a peak meter in series with the TES and measuring the current. And the TES counting rate are the red points, and they were obtained simply counting how many signals were detected in a precise time interval. And as you can see, these two different methods of measure electron give us the same exponential trend, which is the smoking gun, confirming us that the signals we were seeing were actually due to these electrons. So for each voltage tested, so this means for each energy of electrons, we acquired an histogram, we acquired the signals, and then we studied the histogram of the amplitudes of those signals. And so here I reported the ones for 96 EV electrons. So what catches the attention here is that we are sending monochromatic electrons on the device because we have fixed voltage here, so fixed electrons energy. And these monochromatic electrons produce very different amplitude signals. So this means that they release a different amount of energy inside the device. Now, the interpretation of this histogram is the following. We have a full absorption peak where the electrons deposit all their energy inside the device. But this peak has two different tails. Now, the left tail is due to partial absorption of electrons. So we are using an electron source much bigger than the TES. So there are a lot of electrons bouncing nearby. And so they undergo different scatterings. They may produce secondary electrons, and they end up leaving just part of their energy inside the TES, which is this tail. But then the right tail of this peak is just influenced by the energy resolution of the device for electrons and the eventual non-monochromaticity of the electron source. But at the electric field and the temperature we are using, we can consider the nanotubes as a monochromatic source. So we directly link the right tail of this peak, so the broadening of this tail, with the TES intrinsic energy resolution for electrons. That's why we decided to study this peak to fit this full absorption peak, focusing on its right tail with an asymmetric Gaussian defined with a right and a left standard deviation. And in particular, so we care about the right standard deviation to understand the energy resolution of the device. And fitting all these different histograms, we found an energy resolution for electrons of 1 eV on 100 eV electrons. And this is how we obtained the resolution. It is defined as the ratio between the right standard deviation obtained from the peak and the mean value of the peak, all multiplied by the electron nominal energy. And we were pleasantly surprised to see that our TES has a compatibility in terms of energy resolution for photons and electrons in the same energy range. The photon data were acquired by an optical calibration of the device. Now, we were surprised. I want to stress this fact that having found such compatibility is noteworthy because at such low energy range, in such low energies, electrons and photons interact in a completely different way with matter. So this may hint that the heat absorption mechanism of the device is the same for both electrons and photons. Okay, so let's conclude. We managed to detect electrons with transition edge sensors, and all these results are in a paper. And the fact that we found a compatibility between electrons and photons casts optimism for Ptolemy, because an energy resolution of 50 milli-electron volts was already obtained with transition edge sensors, with photons of 0.8 EVs, not 10 EV photons, but we are still optimistic about it. And I just presented you the result of my master thesis. We are going on with these measurements, and we obtained latest measurements with a really improved spectrum. Here you can see that the full absorption peak is much more defined, it's more symmetrical, and it's much easier to work on. And we also improved in terms of energy resolution. And we are preparing a paper about it to show our improvements. So that was all. Thank you for your attention.
Thank you, Benedetta. Other questions? So on the previous slide, you had like this oscillation spectra. How's these oscillations on the left-hand side?
This one?
Yeah.
Okay. Let's see if I have something in a backup. I think, okay, this is good. Don't worry about the electric field, this is good. So when we use photons on a transition edge sensors, we see the Gaussians related to how many photons hit the device in a Poissonian envelope. Now here you can see the 0, 1, 2, 3 photons, but in this other figure, oh no, this one, we have seen 30, 31, 32 photons. So you are seeing the tail of a Poissonian, which is much, yeah. Yes, exactly.
All right.
I was wondering, we Ptolemy have any kind of angular resolution? Will it be able to distinguish from which direction the relic neutrinos are coming from?
This is something we are talking about. I mean, relic neutrinos will be in a more advanced stage of Ptolemy because of some problems, but there is the thought of directing in a different way the electron source. We will have some kind of angular, I don't think if I can call it resolution, because the fact is that the electric field used to collect electrons will select only part of the electrons. So half of the solid angular electrons will not be taken, let's say. So we will be sensitive to an hemisphere of a solid sphere. But then I think that directing it in different way, we can do some differential measurements and try to understand something about the direction. And also the capture rate of fermions depends on the direction in terms of its spin. So placing the detector, the target in different direction, in different orientation can modify the event rate. So we could manage to add something about also the direction of the relic neutrinos. But this is not the goal of the experiment. So there is not something we are thinking too much about.
Thank you. What is the prospect just in terms of sensitivity to the number density for such technology? You know? Hundreds per centimeter cube per flavor.
Yeah. Okay. I can tell you that in the final Ptolemy experiment, there will be 100 grams of tritium, which would lead to, I think, order 10 events per year.
Yeah.
So maybe something can be
for a baseline of 100 neutrinos around us per centimeter.
Yes.
I know that sometimes.
Yes, it changed. Yes, we are, of course, we have different models in terms of Majorana or Dirac neutrinos in terms of rate. So also simply seeing how many captures we have, maybe we can also say something about it.
Thank you.
Okay, let's thank Benedetta again.